what I'm going to talk with you about in the next few minutes is my ideas of what the elements of an accurate production forecast are without being real specific, just what fundamental things should be there if your forecasting has a good chance of being accurate. All right. Why not just put your data in some rate versus time data matching procedure? Well, there's a problem in doing that. So let's look at what the problem is. You know, these production forecasts that we make, I think as we all know, that really is the basis for our reserves estimates. And unless we have some controls on our forecasting methods, those estimates, those forecasts can be inaccurate, and that means inaccurate reserves, inaccurate year-by-year production for economic analysis, and that's going to lead to inaccurate property valuations and reserves reporting. So there's a strong reason to say we need to try to find forecasting methods that are as accurate as we can. Okay, so given that we have a problem that if we don't think it through carefully, we can have inaccuracies, then what can we do about it? There's been a lot of work going on in the old tried and true decline curve analysis business, particularly in the last 10 years as the unconventionals have become so important. I want to look with you at some of the findings that I think provide the elements of accurate forecasting. Very importantly, it's important to identify distinct flow regimes in production data. Major flow regimes, first, at earliest times in a really low permeability reservoir, say a horizontal well with multiple fractures, there's going to be transient flow, and by transient flow I mean flow that has not been affected yet by reservoir boundaries. Then later, the second really major important flow regime is flow that is influenced by the boundary, and the decline models for these different flow regimes will be different. We can't just use, if we want to be accurate, the same decline model for both that early transient flow and then the later flow that's been influenced by the boundary. So what we have to do is find parameters. Most people use the ARPS decline model, for example. Find parameters in the ARPS model that work during that early flow regime, and find parameters in the ARPS model that work later once we have influence by the boundaries. A second principle here, the most recent data is the most important, and we need to give that higher weight. If early on we saw transient flow, and then we see the influence of boundaries later, you know, it helps our understanding to know we've seen that transient flow early, but we don't want to give it much, if any, weight in matching these later data influenced by the boundaries, because that's what we're going to need for forecasting. We need to model that later data accurately. So again, in general, I'd say the most recent data is the most important, and that's something that we need to do. There's another problem, but at least if we identify it, it's part of our solution, and that is if we expect the flow regime to change in the future from what it is now, then we need to do the best we can and figure out when that change is going to occur and include that in our forecasting model. And then my final point, we need to make sure that the decline curve analysis software that we use includes all these elements, and better software will. If we adopt these elements, what kind of benefits will we get? Well, first and very importantly, we'll get more accurate forecasts. we'll be better able to assess property values. And we'll have more accurate inventories of our reserves and other resources. And, you know, that's really our goal, to try to do this as accurately as possible, to put the most accurate possible value on those resources. All right, I said first we need to identify flow regimes. How can we do that? I know it's an extra step in decline analysis. It's worth spending the time to do this. Basically, what I have shown here is this is basically a rate versus time plot for production data. It's really the reciprocal rate because it's going up with time. We identify the different flow regimes. They have characteristic signatures on this kind of plot. The transient flow early is almost always linear flow. Linear flow from the reservoir into these fractures in our horizontal wells. And the signature is almost always a straight line with a slope of 1/2. So if we just make this plot and identify this, we can find when we're in transient flow and model that appropriately. The next flow regime that's really important, I'm going to skip some of this intermediate stuff, but the next one that's important is the characteristic shape once we have fully felt the effects of the boundaries. And on this kind of plot, we get a unit slope, a straight line with a slope of 1. You know, double the slope that we saw earlier. This is pretty simple and pretty straightforward. Again, it's an extra step, and in my judgment, it's a step well worth taking. Here's an example of a well in Eagle Ford. And most of the wells have these characteristics. Here's our early slope of 1/2 on the reciprocal rate versus time plot. We haven't felt the effects of boundaries yet. And then here's the later data that can be fit reasonably well with a slope of 1. Okay, what should we do for forecasting if we got this much data? What happened here really doesn't matter. We need to project this trend into the future. What if we're back here? Well, we've got some more linear flow. We've got to figure out a time at which to switch from this to this and use that for forecasting. If we don't, our forecast won't be as accurate. So that leads us to the final step, which is forecasting. Here is an example. Data pretty free of noise for illustrative purposes. This is a plot not of reciprocal rate, but just gas rate versus time. Here's that early slope of 1/2. And let's say all the history we have goes to here. Now, one of my principles was fit your most recent data, your final data. Well, our final data is still in linear flow. So for a while, we're going to stay in linear flow. We have to make an estimate of when we're going to switch out of linear flow and begin to feel the influence of the boundaries. And, you know, if we haven't seen it yet, we must make an estimate. But that's part of a forecast that really is as reliable as we can make it. So we're going to have to make an assumption about when we will begin to see the effects of the boundaries and then forecast from that point forward. So some linear flow remains, some flow influenced by boundaries, and then full influence of boundaries later. And for the forecasting, we'll need to select the appropriate ARPS B value for that final forecast. All right, here's another example with some less ideal data. We have begun to see the effects of the boundaries in this particular case, but we've just begun to see the effects of the boundaries. What's going to happen in the future? We've got to make a judgment. I show two different forecasts here. One, which might be appropriate for a kind of a homogeneous reservoir with an ARPS B of 0.5. That's this curve here. If it's more heterogeneous and we know our geology, we might forecast with an ARPS B of 0.8 for the remaining life of the reservoir. It's a judgment call. that we have to make. But we need to be conscious of the fact that we've got to make that judgment, and it is going to affect our final answer. Okay, so to summarize quickly what I've tried to say, to ensure that we have the most accurate forecast that we can come up with, we need to identify flow regimes. That's probably the single most important step in doing forecasts accurately. We need to fit our final flow regime that we've seen, the most recent history. That's really important. What's happened earlier really doesn't matter that much. It provides understanding, but it's not something that really ought to affect our forecast. And then in the forecasting, if we have data already in boundary-dominated flow, that's my acronym BDF, we need to select the most appropriate final B value. And that's going to come from experience, judgment, and analogy. If we're still in transient flow, we've got a bigger problem. We've got to choose the end of that flow regime and then make our best judgment as to what the final B value will be once we get into those data that are influenced by the boundary. So how do we do this? Preferably by analogs, other wells in the same area with longer histories. If we don't have any wells with longer histories, we're going to have to use reservoir models. Just put in our best guess of what those reservoir properties are, run models, and see when we expect to change flow regimes and what the final trend will be. And my final point is, we really help ourselves if we let good software help us do all these things quickly and accurately. Because I realize that these steps are sort of easy to describe, but if we have lots of wells, we have lots of work to do. We need to find software that can help us with a big part of this burden in going through all these steps. Okay, so that completes my discussion. If you have any questions or comments, I'd be happy to address them.